Thank you. I guess I stand between you and lunch. It's usually not a really good position to be in. So my name is Eelke, University of Nevada. So I'm here to talk about our note on omnidirectional navigation using head-tilt. So with over 2 billion smartphones in the world, mobile VR platforms like Google Cardboard or Gear VR have the largest potential to bring VR to the masses. Now, when moving around freely has been a fundamental appeal of 3D video games for decades, facilitating this in VR has been a challenge, especially on mobile VR platforms, because their input options are fairly limited. Popular mobile VR platforms like Google Cardboard also kind of require controller-less forms of locomotion, as a smartphone adapter needs to be held with both hands to minimize cybersickness. Recent mobile VR platforms like Daydream or Gear VR feature a controller, but controller-based navigation is still kind of experiencing a number of problems because the optical flow that gets generated during locomotion can kind of act like a double-edged sword. Where the presence of optical flow during directional navigation can cause cybersickness, so a better solution would be to use teleportation, which instantly translates the viewpoint, which doesn't have or doesn't generate optical flow, does minimize the cybersickness, but the lack of optical flow also limits path integration, which can then cause spatial disorientation. So primary reason for cybersickness, and this has been mentioned before in other talks, is a sensory conflict between the visual, vestibular, and proprioceptive systems. So optical flow cues kind of provide the user with the illusion that they're moving, but when a user is using a controller, they're standing still, so there are no vestibular or proprioceptive cues that are generated, which then causes your body to become confused and experience cybersickness. So quite a few approaches to solving cybersickness involve reducing optical flow and reducing the field of view, but this can be kind of detrimental to presence. So my lab has been kind of pursuing an alternative strategy where we're trying to kind of explore locomotion solutions that generate vestibular and proprioceptive cues so your body doesn't get confused in the first place. So I think we all agree that no one really gets cybersick from real walking, but this isn't available yet on mobile VR platforms because they don't feature positional tracking. So the question is really, how closely can we approximate walking without running into tracking space limitations? And if you look at walking more closely, you can see that it generates proprioceptive cues like head bobbing, arm swinging, gait rotations, knee raises. So at CHI last year, we presented a walking in place technique called VR Step that uses inertial sensing and which basically lets users navigate by providing step-like motions while remaining stationary. So benefits of this technique are that it's hands-free and it also generates some of these aforementioned proprioceptive cues, which leads to a higher presence, better spatial awareness, and minimizing cybersickness compared to controller input. But a limitation of walking in place is that it only navigates users in the direction of their gaze. So in this game, when I'm kind of getting too closely, I kind of have to I can't navigate backwards. I have to turn around, do a 180, move forward, do another 180. So that kind of leads to inefficient navigation. Going back to our walking person, walking also generates vestibular cues because as a result of bipedalism, humans tend to kind of lean their body in the direction they walk to align themselves with the gravitational vertical. And you've probably seen interfaces like this, these popular hoverboards. They kind of exploit leaning interfaces. And leaning interfaces have also been explored for VR. And studies have found that they are slightly slower than using a joystick, but they offer higher presence because of these vestibular cues. So for mobile VR context, leaning interfaces have promise and potential because they're hands-free, they offer omnidirectional navigation, but they're fairly difficult to implement as they kind of rely on bulky sensors because we're trying to measure whole body tilt. So in this node, we're kind of taking a little bit of a simpler approach. We're trying to measure just using head tilt, because it can be easily measured using the smartphone's inertial sensors. The implementation details can be found in the paper, but it does require a trade-off between the amount of effort you have to do to lean in a direction versus the freedom to be able to look around without moving. And obviously what we're trying to do here is to kind of make walking in place better by augmenting it with head tilt. So the idea is you basically control velocity using your step frequency, and then the direction is basically indicated using head tilt. And this actually would, where walking in place already fairly closely imitates walking, adding this vestibular component to it would actually make it approximate real walking even more, and thus could probably lead to a higher presence. So we did a user study to evaluate the effectiveness of head tilt. And we kind of designed a navigation task that was kind of inspired by a task that is kind of a standardized task for testing bipedal robots. So we kind of figured that should work definitely for humans. And this kind of requires navigating through a corridor while avoiding obstacles. So that does involve lateral motions. We tested 3 different techniques. So we did walking in place, the modified version with tilt, tilt by itself, and a joystick, and then we measured the completion time, number of collisions, and we measured cybersickness using the SSQ questionnaire and some other qualitative feedback using a questionnaire. So here's a little movie of me using the augmented version of walking in place with tilt, and this is tilt by itself. So just lean in a direction. There's also kind of a little visual cue that kind of indicates the direction of leaning to help users. So this table shows the quantitative results. So surprisingly, tilt was significantly faster than both the augmented version of walking in place and joystick, and also led to far fewer collisions. So this is a very surprising result. I hadn't expected this. But later on, we kind of theorized that this could also be because, we already do steering with your head. So when you also do velocity control with your head, there are just shorter neural pathways for your body to perform than when you control velocity either using a joystick or using walking in place. Another result is that walking in place, our augmented version, offered the same performance as a joystick, and though previous studies have compared walking in place with a joystick and also found similar performance, these studies have always involved forward-based navigation tasks. But when you navigate in VR, you move forwards, sideways, backwards. So we explored lateral motions and we found a similar performance. So that's a good thing. We also did not notice a significant difference in cybersickness. Actually, none of the techniques caused significant levels of cybersickness, or at least very low levels of cybersickness. So qualitative results, overall, tilt was found to be most efficient and was liked the best, with joystick control was least liked and had the lowest presence. So just to summarize, here's a little table that kind of shows the benefits of all the techniques that we tested, which you can kind of add to your Locomotion toolbox if you want to. So both tilt and our augmented version of walk in place offer hands-free interaction. They don't require any instrumentation. They do not cause cybersickness. And then tilt offers the best performance, with walking in place tilt the highest presence. I do have to say that if you use tilt by itself, it does affect your ability to be able to look around freely. So tilt cannot be used for applications like puzzle games that require you to look around a lot. Another thing that's interesting, both tilt and the augmented version of walking in place can be easily integrated in existing positional tracking systems. So if you want your users to navigate beyond the confines of available tracking space, they can easily switch to one of these techniques. And that's it.
We have times like 3 minutes for the questions.
Hi, Steve Feiner, Columbia University. Interesting results. Can you tell me how long people were in VR during the experiment? I couldn't find it in the paper.
They were about, they did 5 tasks times 3 different navigation techniques, and every task lasted about 40 seconds, so it was about 15 minutes, and then we took breaks for them to fill in this SSQs. So, yeah, they weren't exposed for super long periods of time.
So this is between subjects or within subject?
Within subjects.
And single session?
Sorry?
Single session?
Yeah, single session.
Okay, because if you do get cyber sick, you would end up having those symptoms through the other conditions as well.
Exactly, but we did have subjects rest for like 5 to 10 minutes if they were experiencing.
5 or 10 minutes is not enough.
Okay.
Another question, I'm a little concerned about your conclusion that there is none, because you eliminated, if I read your paper correctly, participants who had previously reported cyber sickness. And there's a lot of variation between people, and people who don't get it, and there are a number of people who don't get affected by it, are obviously not going to get affected by it. But people who do, you've now eliminated.
Well, it was kind of one of the requirements of our IRB that we didn't want to, people that had previous experience, we didn't want to have them, terminate the experiment early on. So we kind of optimized for all of them being able to successfully complete the experiment. So we did screen participants on susceptibility to cyber sickness.
Right, but that does need to be very clearly stated when you come up with a result like that.
Absolutely, and I did state it in the paper, but because I only had 10 minutes for this talk, I couldn't state it.
Okay, thank you.
Here. Thanks.
All right, let's thank you for our speaker again. So they will transform